Hi, welcome back. We're going to review some spherical and cylindrical coordinates and tangent and normal binormal vectors. Now, I'm just going to work a few of these problems with you just so we can remember how to do some of them. So I'm not going to be able to work all of them today, but we can take a look at a couple of them. So if we were to take a look at number 1, it says, what is the following implicit equation of the graph? And notice they give us this z equals x squared plus y squared. So if I want to find out what this is, first thing I'm going to do is I'm going to square both sides, give it the square roots, and we would get z squared equals x squared plus y squared. And of course, bringing the x and y's over, we would get z squared minus x squared minus y squared equals 0. Or we would get x squared plus y squared minus z squared equals 0. And we should recognize this as a elliptical cone or an elliptic cone. So I guess I could write it up here in the spot in the elliptic, there we go, cone. And be careful, the original, remember, we're only looking at the square root, so we're really only looking at the top half of an elliptic cone. So if I wanted to sketch the graph on the domain right here on the xy plane, this is an elliptic cone, and it's going to open up along the z-axis, because remember, that's the odd man out, it opens on z. Now typically when we graph an elliptic cone, it would look something like this on both sides. It would look like so. However, we only want the top half, so we just get rid of the bottom part right there, and our elliptic cone would kind of look would just be the top part of a cone, something similar to this. So for question number 3 now, we want to write this in cylindrical coordinates. So we might remember for cylindrical coordinates, if we're given z equals the square root of x squared plus y squared, well, we already know, we should remember from cylindrical coordinates that r squared is x squared plus y squared. So I could therefore write this as z equals the square root of r squared, because x squared plus y squared equals y squared, or I can just say z equals r. To write this in spherical coordinates, let's go and do that one. Remember, that's a little bit tougher right there. But let's see here. Let's go down to question number 5. We want to write the equation of our sphere with radius 8 centered at the origin in spherical coordinates. So this is just basically saying rho is 8, and that's all we have. So in spherical coordinates, this is just basically saying rho is 8. And again, how we get that, remember we got x squared plus y squared plus z squared equals 64. And remember, x squared plus y squared plus z squared, this is just saying rho squared is 64, or rho is 8 right there. And let's see here, let's try to practice writing another one in. So try number 6, go ahead and write that in cylindrical coordinates for you if you'd like. And let's take a look at question number 7 real fast together. So do this one on your own. There are the answers on my online if you want to take a look at it. So if we look at a question like number 7 now, where we're asked, given the following vector equations, we want to write the unit tangent vector. And it's pretty nasty. Remember, to get the unit tangent vector, this is just r prime of t divided by the magnitude of r prime of t. So we're going to just take the derivative, and be careful with natural log. This becomes 1 over t cubed, so the key t cubed on bottom. Chain rule, don't forget there's a chain rule there, so I'm going to multiply that by 3t squared, comma. Over here, when we take the derivative of 6 root t, sorry, I think my focus is way out of whack there. So if we take the derivative of t root 6, remember that's just going to become the square root of 6. Don't let that radical confuse you. And for the last one, for the k's, if we take the derivative, we're going to get just t for here. and then we just divide by the magnitude. Nothing pretty. This isn't going to turn out nice because remember, r prime is not constant, so the magnitude is not going to be constant. It's just going to be very pretty. I can simplify the top up over here. This is just 3 over t. So when I square that, that's just 9 over t squared plus 6 plus t squared. And we can leave that alone in terms of our unit tangent vector. Alright, so for the next few, we want to convert the points into spherical and cylindrical coordinates. So let's just take a look at number 8, just a kind of a quick review for us. Alright, so if I want to convert this one into spherical coordinates, remember, rho, we need theta, and we need phi. So, looking at the old formulas, to get rho is just the square root of x squared plus y squared plus z squared. So that's just going to become root 2. To get theta, remember, to get theta, if we look over here, real quick, look up over here, sorry. Let me get another sheet of paper up there for you. Remember, when we look in spherical coordinates, on the xy plane, that's how we get our angle theta. To get phi is measured from the positive z-axis, so that would be phi right there. Right. So to get theta, we're looking at the inverse tangent of y, the inverse tangent of y over x, just like we would do in polar coordinates. So this becomes the inverse tangent of 1 over 1, which is pi over 4. Now be careful of your quadrant. I know I'm in 1, 1, 0, so I already know my quadrant right there. Now, phi, to get phi, this was the arc cosine of rho over, z over rho. Sorry about that. Arc cosine of z over. So, and since z is 0, we're really looking at the arc cosine of 0. Whoops, of 0, and that's going to give us pi over 2. Remember, phi is restricted between 0 and pi. Theta has restrictions from 0 to 2 pi. So in spherical coordinates, we would get root 2, pi over 4, pi over 2. There's our spherical. And to get cylindrical, kind of running out of room here, to get cylindrical, we need r, theta, and z. So z is just 0, r is just the square root of x squared plus y squared, which is just going to be 1 plus 1, which is root 2. Theta is just the inverse tangent of y over x. Again, it's the same tangent from spherical, which becomes pi over 4, and we would get root 2, pi over 4, 0. We have a whole formula sheet on these, so make sure you go back and take a look at those, okay? All right. So, let's take a look at one more example right down here. And let's see here, number 12. For number 12, let's practice finding the unit tangent vector again. So to get the unit tangent vector, we would want r prime of t over the magnitude of r of t. Now if we remember, this is our spiral, so these are nice because we know that the magnitude is going to be a constant. So this is going to be negative 2 sine t to cosine t 2 divided by the magnitude. Now we should be getting pretty good at this. This is just a circle, so this is just going to be 4 sine squared plus 4 cosine squared, which is just 4 plus 4, or root 8. And there is our unit tangent. To get the unit normal vector, remember this is a constant, r prime, the magnitude of r prime is constant, which we like, and because of that, we can use our shortcut to get the unit normal vector, which would just be the magnitude of, the derivative t prime t over its magnitude, which is going to be negative 2 cosine of t, negative 2 sine of t, 0 over root 8, right? But then I got to divide by its magnitude. Well, the magnitude is not going to be too hard. This is just going to be the square root of 4 over 8. Right here. And of course, the root 8's cancel, the 2's will cancel, and what we're left with is just cosine t, negative cosine of t, negative sine of t, 0. And there we have that. There we go. Ran out of room there. And to get the binormal vector, we're not going to finish up the binormal vector here, but we can kind of get started. To get the binormal vector, that is just going to be our unit tangent crossed with our unit normal vector. Now, look for the binomial, not the unit binomial, just the binormal vector. That's what I'm going to give you today. Alright, so I hope you guys had fun with the video. I did, and I'll see you guys later. Bye-bye.